Thermodynamics describes the transfer of energy as work and heat. The first law of thermodynamics, or the law of conservation of energy, says that energy is neither created nor destroyed. It's just converted between work and heat. When work is done on a system, or it gains heat, its internal energy increases. When a system does work, or it loses heat, its internal energy decreases. To calculate the internal energy of a system, we add together heat and work. But make sure you're using the correct signs for each. When heat is absorbed by the system, Q will be positive. When heat is released by the system, Q will be negative. When work is done by the system, like an expanding gas, W will be negative. When work is done on the system by the surroundings, like gas compression, W will be positive. Our example says an exothermic reaction releases 100 kilojoules of heat and a gas is produced that involves 10 kilojoules of work. Since our reaction is exothermic, Q will be negative. And since gas is being produced, W will also be negative. The second law of thermodynamics says that the entropy of an isolated system only increases. Entropy is essentially randomness or disorder. More entropy is a lower energy state, so things tend to move towards that lower energy state or disorderliness. The example I like to use for this is trying to keep your room clean. It'll naturally tend to get messier unless you put the work into cleaning it and keeping it orderly. The third law of thermodynamics says that the entropy of a perfect crystal at absolute zero would be exactly equal to zero. An example of this would be a perfect diamond with absolutely no impurities at 0 Kelvin. And remember, at absolute zero, you would have no kinetic energy and no movement whatsoever, which is essentially impossible. But if it were possible, then the entropy would be equal to zero.